Welcome back to more of my biopsychology lectures. In this series of lectures now, I'm going to talk about the nerve impulse. I'm going to talk about these separately. I'm going to start with a resting membrane potential, talk about how that facilitates the action potential. The action potential occurs in the axon hillock, a small part of the neuron. I'm going to talk about how that moves to the axon terminals so it can send information to other places. Talk a little bit about the myelin sheath and local interneurons. I'll do that in the context of the action potential. For this video, I want you to be able to explain the forces, both the electrical and chemical forces, acting on sodium and potassium ions. I want you to be able to tell me what a membrane potential is and explain how the resting membrane potential is established and maintained. This is critical. You all know that if electrolytes get off balance, you die. Part of the reason is because the nervous system no longer works correctly. Now, when we talk about cells, you have to go back and remember the cell membrane. Okay, so this is a cartoon of the cell membrane. Sometimes this is called the plasma membrane. There's several different names. But basically, it's a fat sandwich. The fat sandwich is phospholipid molecules. These are going to cover the whole cell. Anything that is lipid soluble, heroin, for example, is lipid soluble. So if I have a heroin molecule sitting around here, it dissolves in fat. So like anything that dissolves in fat, right, that means it can just pass right through it. So things that are lipid soluble, things that are so-called lipophilic, can go right through the membrane and into the cell. Okay, that's important when we talk about drugs later, not just drugs of abuse, but just in general. Other things like sodium ions, these can't just flow through the fat sandwich. Okay, it's like trying to mix water and oil. Okay, the sodium can't go through. Okay, so what we have is a membrane, a fat sandwich basically, that lets some things pass, but other things can't pass. That means it's semi-permeable. Semi means partially, permeable means things can pass through it. Now that's just the membrane. Obviously, you know lots of things are going to flow in and out of the cell. In order to do that, they're going to need help. And almost all the help comes in the form of protein molecules. Here is an example of a channel. Okay, so a channel is basically a tunnel through the membrane. Let's say this is a sodium channel. Now, if I've got a sodium molecule here, can it go through this? No. But the sodium molecule can pass through this tunnel. Okay, so my sodium molecule can come into and out of my cell depending on if there's a channel for it. Now, for anything that passes, things like water, there's going to be a channel. For water, there's a special class of tunnels, of channels called aquaporins. Okay, so water, H2O, can always flow through the membrane. It doesn't go by passing through the fat sandwich part of it. There's special proteins that are always open. So if they're always open, water can always go in and out. Now some channels, like sodium channels, potassium channels, many other channels, sometimes they're open and sometimes they're closed. So if this channel's open, sodium can obviously flow right through it. What if it's closed though? I put a nice big gate here. Now, can sodium flow through? No, obviously it can't. Okay, so there's going to be a gating mechanism. Gating refers to open or closed. Some of these channels are closed most of the time. So we're going to talk about voltage gated sodium channels in a bit. Those channels are normally closed. Under special circumstances, they can open up and then ions are going to flow through. Okay, so basically we have this fat sandwich covering all cells. It's semi-permeable. Things that are lipid soluble, things that dissolve in lipids like heroin, can go right through it. Okay, they don't obey, they don't need tunnels, they can just go right through. They can't be regulated very easily by the cell. Other things, sodium, potassium, neurotransmitters, glucose, all kinds of things that the cell needs, can't just pass through. They're always going to need these protein molecules. Some of these protein molecules are going to be channels that are basically tunnels through the membrane. Okay, other things like glucose, we'll get into glucose transport a little bit later, but that's going to be different. Okay, but it still needs protein to help it get through. Now, what is an electrical potential? This is quite simple. It's just a separation of charge. Okay? Now, you're familiar with this with batteries, right? I'm not a great drawer, especially trying to use this pen. All right, but here I got my battery. Here's a positive end. Here's the negative end. Okay? Now, if this is a typical battery, let's say it's 1.5 volts. Okay, so if you have a 1.5 volt battery, there's a positive end and a negative end. What if you put that into your device opposite? It doesn't work, right? Okay, what this separation charge allows is for charges, you know probably already that like charges are attracted to one another. Okay, so basically, if we have a separation of charge, these things are going to want to move. Okay, and there's a force driving their movement. When they move through the circuits, the wires of your device, that's actually going to do work. That's what powers your device. When there's no longer a separation of charge, when all the ions have moved, so now that there's no pressure, no force driving it, now your battery's dead. Okay. Now, one thing, the separation of charge, how much charge is separated, is measured in volts. Okay. The bigger the number, the greater the separation of charge. Okay, so a 1.5 volt battery doesn't have nearly as big a separation of charge as a 9 volt battery or a 12 volt battery. Okay, so the potential to do work is much less, obviously, in your 1.5 volt battery than these other batteries. Now, in neurons, we are going to talk about electrical potentials, but we're not going to use volts. We're going to use millivolts, MVs. Okay, so electrical potential is just a separation of charge. The more charge that's separated, the more work that can be done. Now, a membrane potential is simply a separation of charge across a membrane. Okay, so instead of being physically separated like a battery, here I've got my cell membrane. Remember, right? It's a fat sandwich. I'm not going to draw them all. Okay, we've got our cell membrane. Let's say I've got more positive charges outside. I've got more negative charges on the inside. Now here I have a potential, right? There's a separation of charge. Instead of being at opposite ends of a battery, it's across the membrane. Okay, so membrane potential just means separation of charge across the cell membrane. The larger the separation of charge, the bigger the number. And as I said before, this is going to be measured in millivolts. Okay, so those are some basic definitions. Now, in neuroscience, the way we measure membrane potential is we're going to try to use basically a scientific instrument, don't worry about it, that's going to allow us to compare the charge inside with the charge outside. So we need two microelectrodes. Micro means small, and an electrode is used to measure electricity. So these are very tiny. They have to fit into a cell. And so basically we'll have one that's inside the cell, measuring the charge, one that's measuring the charge outside. And by comparing those, we can tell how much charge is separated, and we're going to put that into a number. As I said, that charge is actually very small separation. It's only millivolts rather than volts. Now, we always talk about inside to outside. Okay, so if I tell you the membrane potential is minus 70 millivolts, this is very important. Millivolts are the unit, right? How much charge is separated. This number tells me how much charge is separated. Okay, now the sign is going to tell me where there's more positive or negative charges. Okay, so if the inside is minus 70 millivolts, that means there's a little bit more negative charge inside the cell than outside the cell. Okay, so if I just give you a number, you should assume it's inside to outside. Now let's just step back for a second though and set that aside for a minute. If the charge inside is minus 70 millivolts, what's the charge outside? Well, how much charge is separated? We know it's 70 millivolts worth. Is the outside more positive or negative? It's more positive. Okay, so this is a little confusing. So if the outside is plus 70 millivolts, the inside is minus 70 millivolts. All right, what's the difference in charge between the inside and outside? This is where you need to think for a second. This is not a number line, right? So we know the difference between minus 70 and positive 70 is 140, right? That's a number line. That's not what we're talking about here. Don't make that mistake. Let's say I add some negative charges or some positive charges to the inside. Okay, so if I add some positive charges, right, there's less negative charges. So let's say now I go to 60. Okay, so it's minus 60 inside. And let's say I keep doing that, minus 30, minus 10. What happens when there's an equal amount of charge inside and outside? What's my potential? Remember, potential is the amount of separation of charge. What if I have an equal number of positive and negative ions inside as I do outside? What's my separation of charge? That's right, now it's 0. Okay, so if the inside's minus 70, the outside's plus 70, what's the difference in charge? The amount of difference is 70 millivolts. All the sign tells you is where there's more positive or negative ions. That's very important. Now, in the membrane, there's a few protein ion channels, okay, as this depicts. Typically, these are fairly specific. Okay, so we're going to talk about sodium ion channels and potassium ion channels. The name of the channel basically tells you what flows through it. So here, in this case, these greens are representing sodium. So what kind of a channel is this? That's right, it's going to be a sodium channel. Okay. Likewise here, the yellow is potassium. Okay, you can see potassium is going to flow out. Now, one thing to remember is that here I have intracellular fluid. Here I have extracellular fluid. Okay, the intracellular fluid means it's inside the cell. Extracellular means outside. The thing to remember is salt, sodium chloride, is more concentrated outside than it is inside. Okay, so basically we're going to be dealing with 3 main ions right now: sodium, chlorine, and then potassium. The way I remember it is the outside is basically salt water, sodium chloride. The inside is going to be the other thing, which in this case is obviously potassium. So you need to remember there's more sodium and chloride ion outside than inside. And I shouldn't say more. The concentration of sodium is greater outside than inside. Same with chloride ion. Okay. Concentration of potassium is greater inside than outside. Now, when these ion channels are open, these things can flow. When it's closed, they can't. Okay, so keep this in mind as we move on. I've got the semi-permeable membrane. I've got special channels that things can flow through. Now there's two forces you really need to understand. One is going to be electrostatic force. The other is going to be the force of diffusion. Okay, these are fairly straightforward. You're intuitively aware of them already, but I'll just make sure that you get them in the forefront of your mind. You know that positive and negative charges are attracted. So if they can, the positive charges will move toward the negative. Now there's a force. If I've got a lot of positive charges, right, these are going to keep moving to the negative terminal. Now, how long are they going to move? Obviously, they're going to keep moving until the concentration of these is equal, until that electrical gradient, the separation of positive and negative charges, is gone. Then they'll stop moving. Okay, that's equilibrium. Okay, so we have an electrical gradient where positive charges are going to try to move toward negative charges. Now, these negative charges can also move toward the positive charges, right? They'll move toward one another. Next is the chemical gradient. Okay, we're all familiar with this. If I have a chemical, chemicals are going to move from high concentration to low concentration. Okay, so if I take some perfume and I spray it up front, initially in the front of the room, right where I am, there'd be a very high concentration of perfume molecules. In the back, there'd be none. Over time, though, they're going to diffuse. Those perfume molecules are going to move. And they're going to keep moving until the concentration is equal throughout the room. Okay, so there's two major forces. Again, electrical and chemical forces. We're going to talk primarily, when we talk about membrane potentials, sodium, potassium, and chloride. Okay, so sodium is Na+, potassium is K+, chloride is Cl-. Now, I didn't write the word ion here, okay, but I'll try to remember to say ion, but sometimes I'll just say sodium crosses a membrane. Here I'm talking about sodium ions, okay? Now, when we look at a cell, okay, this is a cartoon, very simplified version. Here's the cell membrane. Okay, this is the extracellular. This is the intracellular. I told you there's a higher concentration of sodium and chloride ions outside the cell than inside the cell. There's a greater concentration of potassium inside than outside. Okay, so if we think just about the chemical gradient and look at the force of diffusion, let's pretend that these things can move freely. If I have a high concentration of potassium inside the cell, and it could move freely, right, there's a force driving it out of the cell. In sodium, that chemical force is driving it inside. Same with chloride ion. Now, with the cell membrane, these things can't move freely. So I'm going to anthropomorphize. Ions don't really have free will or anything like that, right? But just for shorthand, which way does potassium want to move? Potassium wants to move out of the cell down its chemical gradient. Sodium wants to move into the cell. Okay, so that's going to be the force of diffusion. The greater the difference in concentration, the stronger the force of diffusion. So if I have, let's say, 2 times as much sodium outside, right, I'm going to have a force driving it in. Let's say I have 10 times as much sodium. And again, I'm talking about concentrations, right? Let's say the concentration is 10 times as much outside as inside. Sodium's still going to be driven in. Okay, but the force of diffusion is going to be greater in this circumstance than it is in the other. Okay, so the greater the difference in concentration, the stronger the force of diffusion. Now, you see this A-. This stands for organic anions, right? An anion is just any negatively charged substance. When you look at things like protein, DNA, lots and lots of other things, right? All of these are going to be slightly negative charge. Okay, that's just the way it works out. Those things never move in and out of the cell. Okay? So these huge molecules, these huge proteins, the DNA, things that stay in the cell, are going to give a slightly overall negative charge to the inside of the cell. Okay? Now, if we look at the ions, we already talked about the chemical gradient, but now let's look at the electrical gradient. Okay, so if the inside of the cell is slightly negatively charged, which way is the electrical force driving chloride ion? Like charges will repel, right? So we'll have an electrical gradient driving chloride out. How about potassium? Obviously it's positive, right? So it'll be attracted. So the electrical gradient, that electrostatic force, is going to be driving it into the cell. Sodium, same thing, into the cell. Now it's interesting in a way, because if you look at potassium, the chemical gradient's going to drive it out. The electrical gradient's going to try to drive it in. So which way, if I just open up a channel, will potassium move? It turns out that this force of diffusion is much, much stronger. Okay, so if suddenly I open up a potassium channel, potassium is going to flow out of the cell, even when the inside of the cell is negatively charged, because this force of diffusion is much, much stronger. In fact, it's so strong that when we talk about movement of ions, I basically want you to ignore this electrical gradient. Okay, now in this case, you can see it's the whole slide is titled Neuron at Rest. It's just sitting there doing nothing. Okay? So when we say neuron at rest, I mean nothing's going on. It's just sitting there, nothing's changing. It's a static situation. All right. Here's a nice figure that really summarizes things for you. If you understand this figure, you're in great shape. Outside, extracellular fluid, intracellular fluid. These big organic anions can't leave the cell. We look at potassium, right? We know the force of diffusion is driving it out, but the electrostatic pressure is trying to keep it in. You can read the rest. Okay, this is a good summary diagram. Stop the video if you want. Take a minute and just look it over. Make sure you understand it. Yet another one, we've already seen this, right? Here we're talking about the distribution of ions. Okay. Here we have closed channels over here on the left. Okay, so sodium wants to come into the cell, right? But it can't. How come? Well, it doesn't pass through the membrane, and this channel's closed. Now, what would happen if we were to open it? If we were to open it, sodium's going to come rushing in. Okay, but normally at rest, that's not the case. It's closed. Potassium is going to, again, want to enter the cell because of the electrical gradient. It's going to want to leave the cell because of that force of diffusion. Okay, now, in this particular situation, there's some potassium channels that are a little bit leaky. So some are going to come in, some are going to be forced out. But as I said, overall, which of these two forces wins? It's going to be the concentration gradient. Okay, so some potassium, yeah, it's going to come in, but more potassium is going to leave. So in the cell at rest, we're going to have a net efflux. E means out. A net efflux of potassium. Okay, it's fairly slow, and it takes quite a while for it to diffuse out, but it does happen constantly. If we don't counteract this, you will die. There's poisons that are going to prevent you from counteracting it, and they end up being fatal. They're pretty nasty drugs. Okay? So although both of these are going on, remember concentration wins. We get a net efflux of potassium out of the cell when the cell's at rest because the potassium channels are a little bit leaky. The sodium channels are not leaky. They are very strong, so we don't get movement of that. Now, as these positive charges leave, this is going to cause problems for the cell, and we need to counteract that. The way it's counteracted is by something called the sodium-potassium pump. All right, this channel, once it is open, it doesn't use any energy. Okay, this is free energetically. It's just passive physical properties, which way potassium flows. This uses a lot of energy. I mean, a lot of energy. Okay, so this costs us energy. In fact, when you're at rest, most of the energy your brain uses is actually operating these sodium potassium pumps. What it is going to do is basically set up the concentration gradient. Okay, so what's happening? Remember, sodium's not moving, potassium is going out. I need, if I don't do anything over time, eventually the concentration of potassium inside and outside the cell will become equal, and I'll be long dead. I need to maintain that gradient. So in order to counteract potassium leaking out, I need to pump it in. Okay, so the sodium potassium pump is going to do that. It's going to counteract that efflux and bring potassium in. It's also going to help keep the concentration of sodium inside the cell less than outside the cell. For this class, though, I really want you to focus on the sodium potassium pump as a mechanism to counteract that leaky potassium ion channel. Okay? Here again is another diagram of it showing that this pump, again, which is a protein, it's a big protein molecule. That pump is going to take 3 sodiums and kick them out of the cell. It's going to grab 2 potassiums and bring them into the cell. Now you may remember ATP is a currency of energy. So in order to do this, I need energy. Okay? Now, over time, let's think about this. What would happen if I have the inside of my cell, right? It's minus 70 millivolts, a little more negative inside. That means there's a little more positive outside. What would happen if I were taking potassium, which is a positively charged molecule, and kicking it out of the cell? In this particular case, right, as we lose potassium, that means I have more positive outside, even fewer positive inside, right? So less positive is the same thing as negative, right? Okay, so in this case, as potassium comes out, that's going to lead to more positive charges outside and fewer positive charges inside. So now, what does that do to my separation of charge? If these are coming out, I'm getting more and more separation of charge, right? So what should happen to this number? It's going to get bigger. Okay, so if I don't do anything over time, because of the way this is going to go, instead of 70, now let's say I have a minus 80, a slightly larger separation of charge. Now, what does this sign mean? Remember, the sign just tells me where there's more negative compared to the other. Okay, so if it's negative, I got more negative on the inside. So the separation of charge is going to get larger. That's going to make the number larger. The inside is still more negative, minus 80. Okay, so as it turns out, we're getting more negative. Okay, this is termed a hyperpolarization. I'll talk more about that later. But hyperpolarization inhibits neurons. Okay, so it makes it harder for my brain to send a message to my lungs, the muscles that control breathing, to breathe. So if I continue to hyperpolarize those cells and I inhibit them, what happens? Yeah, they stop telling my muscles to coordinate. I stop breathing and I die. Okay, so if we do nothing, again, the neurons are going to get more and more inhibited, and eventually you're going to die. It's the job of the sodium potassium pump to counteract those leaky potassium ion channels. Okay, so that's the membrane potential. Next time, in the next video, I'm going to spend some time talking to you about the action potential.